Look up toward Jupiter. One moon there is doing something it shouldn't. A ribbon of red light circles its pole. Physics has a number for how far that light should swing. 6 degrees. It only moves 2. That gap sounds small. It isn't. Hubble measured Ganymede's Aurora between 2010 and 2011. The missing 4 degrees looked, for a moment, like a crack in physics itself. Not a rounding error. Scientists checked. They insisted on that. A calculated prediction, built on solid electromagnetic theory, quietly refused to match the sky. Here's the obvious guess. Jupiter's moons are too extreme for ordinary physics to survive. Volcanoes hotter than Earth's, ice shelves hiding oceans, magnetic fields violent enough to fry a spacecraft. Surely something out there finally broke a rule. It didn't. What actually happened is stranger and more satisfying. The prediction failed because something invisible was hiding beneath the measurement. Finding it meant uncovering a hidden ocean nobody could see. 60 miles deep, sealed under 100 miles of ice. 3 moons share the same violent neighborhood. Jupiter's magnetic field is the largest structure in the solar system. Only the sun's outer envelope is bigger. It rotates every 9.9 hours, dragging a colossal magnetic bubble with it. All 3 moons orbit inside that bubble. All 3 are bathed constantly in radiation and magnetic force. Jupiter dwarfs everything else discussed here. It's more than 1,300 times the volume of Earth. Its great red spot alone could swallow our entire planet with room left over. Everything happening to these 3 moons plays out in the shadow of that scale. Ground-based astronomers actually detected radio bursts from Jupiter back in 1955. Nobody understood the cause at the time. It took the Pioneer and Voyager missions, decades later, to reveal the reason. Jupiter's own magnetic field, sweeping charged particles into violent static. That field is roughly 10,000 times stronger than Earth's own, by most estimates. None of them sit in calm, empty space. Jupiter itself is more than 300 times more massive than Earth. Its magnetosphere would look bigger than the full moon in our sky, if you could somehow see it. Inside it, charged particles get trapped and accelerated to enormous speeds. Ganymede sits roughly 6,650,000 miles out, far enough to dodge Io's worst radiation, close enough to still feel Jupiter's magnetic heartbeat every 9.9 hours. That single fact is about to matter far more than it seems right now. Consider how strange this entire method actually is. Nobody flew a probe into Ganymede's ocean. Nobody dropped a sensor through the ice. The whole discovery rests on watching light swing in a telescope, millions of miles away. You don't need to touch something to know it's there. You just need a prediction precise enough that reality can contradict it cleanly. Start with Io, the closest of the 3, and the most dramatic on the surface. Io orbits Jupiter at roughly 262,000 miles. That proximity comes at a violent cost. Jupiter's gravity squeezes Io's interior over and over, like a hand crushing a rubber ball, again and again. The result, a moon covered in more than 400 active volcanoes. In August 2001, Galileo flew just 120 miles above Io's surface. It caught a plume rising over 300 miles high from a volcano nobody had ever cataloged before. That plume stood roughly 10% taller than anything recorded there previously. Picture a jet climbing nearly halfway to where the space station orbits Earth. Except this happened on a moon a third of our moon's size. Galileo didn't just photograph it. It flew directly through fresh volcanic particles. Tiny sulfur dioxide snowflakes struck its instruments in real time. Nobody expected this from Io before Voyager arrived in 1979. It's barely a third the size of our own moon. Small, cold, rocky worlds are supposed to have gone geologically quiet billions of years ago. Io broke that expectation completely, and the reason took years to work out. It sounds like something that shouldn't be possible on a small, cold moon, and yet it's entirely explained. Io's violence isn't a mystery. It's tidal heating turned up loud. Europa and Ganymede tug on Io in a precise 4-2-1 orbital resonance. For every 4 orbits Io completes, Europa completes 2, and Ganymede completes exactly 1. That locked rhythm keeps flexing Io's interior, long after Jupiter's gravity alone would have let it cool. The mathematics behind that resonance dates back to Laplace in the 1700s. He had no idea it explained volcanoes. It took 2 centuries to connect the two. Voyager 1's surprise 1979 photo of an eruption finally did it. Extreme, yes, but never once a violation of anything physics predicts. The 4.2.1 resonance locking these moons together is remarkably stable too. It's survived for likely billions of years, since not long after the moons formed. That kind of long-term gravitational lock is rare in the solar system. Most orbital arrangements drift apart over time, not lock in place. Maybe it isn't Io, maybe it's Europa. Europa sits one shell further out. Its cracked ice hides a salty global ocean, 10 to 15 miles down. That same tidal squeezing keeps it liquid, just gentler here. In December 2012, Hubble's imaging spectrograph caught something above Europa's south pole. Hydrogen and oxygen glowed faintly above the pole. It looked exactly like water vapor venting into space. The plume appeared to reach roughly 200 kilometers high. For over a decade that finding held. Confidence in the plume sat near 99.9%. Further Hubble looks in 2016 and 2017 seemed to confirm it. It felt like settled science, a moon quietly leaking its ocean into the vacuum above it. Then in 2026 that confidence collapsed. Kurt Rutherford's team at the Southwest Research Institute went back through the same data. They published their findings in Astronomy and Astrophysics. They found interference from Earth's own upper atmosphere. It had contaminated a signal already traveling 400 million miles. Once removed, the plume's confidence dropped below 90%. A decade of headlines may have been chasing a shadow. Consider what a decade-long confidence collapse actually costs a field. Grant proposals get written assuming results like Europa's plumes hold up. Mission designs sometimes bank on results holding steady for years. When a pillar like that wobbles, entire research programs have to recalculate. That's a real scientific walkback, not a footnote. The original 2012 detection was led by Lorenz Roth. It shaped mission plans and textbook chapters for years. Rutherford wasn't some outsider looking to make headlines. He'd worked with Hubble's ultraviolet instruments for over a decade already. Reopening a decade-old celebrated result takes a specific kind of nerve. It means risking your name against a finding the whole field already believed. He simply rechecked something nobody had questioned in a decade. That's exactly how good science is supposed to work. Even if Europa's plumes turn out real, they still aren't a broken law. They'd follow the same tidal heating mechanism as Io, just weaker and harder to catch. Unconfirmed, contested, still genuinely uncertain, but never impossible. Europa isn't the anomaly either. The story moves on. Compare that to Europa for a moment, where the debate still rages. Europa's ocean claim depends on plumes that may or may not exist. Ganymede's ocean claim depends on two independent measurements, agreeing with each other. That's a meaningfully stronger position to stand on. That leaves Ganymede, and Ganymede is built differently from both its neighbors. Ganymede generates its own magnetic field, not one induced by Jupiter, the way Io's and Europa's likely are, one manufactured internally inside the moon. NASA's Galileo detected it directly in 1996, using its onboard magnetometer. It was the first magnetic field ever found around a moon, not a planet. Galileo itself deserves credit here too. Launched in 1989, it survived radiation levels that would fry most modern electronics. Its magnetometer was simple by today's standards. Yet it delivered one of the mission's most important discoveries, a moon, generating a magnetic field entirely on its own. That field creates two glowing rings of Aurora, circling Ganymede's poles. They sit inside Jupiter's own far larger magnetic bubble. Here's where the physics turns specific. Ganymede's field doesn't exist alone. It sits nested inside Jupiter's enormous spinning field. Picture a small compass beside a much larger rotating magnet. As Jupiter completes each 9.9-hour spin, its field should tug Ganymede's rings, rocking them back and forth around each pole. Physics gives an exact number for how far, roughly 6 degrees, calculated from known field strength and geometry. Not a rough guess, a clean testable prediction with one specific answer. That 6-degree number wasn't pulled from thin air, worth stressing. It came from decades of prior work mapping Jupiter's field in detail. Every prediction in this story rests on earlier predictions, tested and confirmed first. Science rarely leaps forward. It accumulates one confirmed layer at a time. Between 2010 and 2011, Joachim Saar pointed Hubble at Ganymede's poles. He worked at the University of Cologne and watched for hours. His team had already spent years modeling Jupiter's magnetic environment before this observation. The 6-degree number wasn't a hunch. It came straight from that earlier work. Saar didn't stumble onto this discovery by accident. His earlier modeling of Jupiter's field made the 6-degree number possible in the first place. Without that groundwork, 2 degrees would have just looked like a random reading. Context turned a strange number into a genuine discovery. Ask yourself what you'd conclude watching that gap. Would you assume the equations were simply wrong? Or would you assume something was hiding just out of view? For one genuine moment, that gap looked exactly like the headline promised. A calculation checked twice over. It simply refused to match the sky. Consider what precision that measurement actually demanded. Hubble had to resolve an angle smaller than a degree, from 400 million miles away. That's like measuring the width of a coin from across a city. Multiple observing sessions across an entire year went into confirming the result wasn't a fluke. The rings moved. They just didn't move far enough. The measured swing came out to roughly 2 degrees, less than a third of what 6 demanded. Saar's team didn't rush to publish a wild claim. They ruled out instrument drift first, then atmospheric interference, then timing errors. None of it explained the gap. Published in the Journal of Geophysical Research, the discrepancy stood, real and repeatable. Hubble wasn't built with Ganymede's ocean in mind either. It launched in 1990, designed mainly to study distant galaxies and stars. Decades later, scientists pointed its ultraviolet instruments at a moon instead. That's the kind of secondary discovery great instruments make possible. Nobody planned this result when Hubble first left the ground, except physics doesn't actually break under pressure like that. It demands a full explanation, and it found one. Only one mechanism closes a gap this specific. Something beneath the surface must be electrically conductive, generating its own weak counterfield, canceling part of Jupiter's pull. Saltwater does exactly that. Think of it this way. Moving a magnetic field near any conductor makes current flow inside it. That current builds its own field, always pushing back. Faraday worked out that principle in the 1830s. It's the same rule that runs a generator. Physicists have a name for this basic effect: electromagnetic induction. Move a magnetic field near any conductor, and current starts flowing inside it automatically. That current then builds its own field, always pushing back against the change. It's the same principle running every generator on Earth. At Ganymede, that same law turned a spinning field into ocean evidence. Picture spinning a large magnet beside a small compass. Calculate exactly how far the needle should swing. 6 degrees worked out from physics alone. You run the experiment, and the needle only moves 2. Every single time, no matter how carefully you repeat it. You wouldn't conclude physics had failed. You'd conclude something invisible near the compass is generating its own counterfield, a hidden sheet of metal perhaps. There's also a reason this specific explanation convinced skeptics fast. A counterfield this strong isn't subtle. It demands a genuinely good conductor, spread across real volume. Pure ice barely conducts electricity at all. Rock conducts a little better, but nowhere near enough. Only a thick planet-spanning layer of salty water fits every constraint at once. That's precisely what Hubble found at Ganymede. The compass is the Aurora. The spinning magnet is Jupiter's field. The invisible metal sheet is 60 miles of salt water, sealed under nearly 100 miles of ice. None of this makes Ganymede's discovery any less remarkable, either. Scientists inferred an entire ocean's existence without a single drop of direct contact. No submarine touched that water. No drill or lander ever reached it. Just light bent slightly out of place, 4 degrees at a time. This conclusion doesn't rest on the Aurora alone. In 2021, NASA's Juno spacecraft made a close flyby of Ganymede. It carried an infrared spectrometer called GRAM. Rather than tracking light in the sky, GRAM scanned the surface directly, hunting chemical fingerprints instead of magnetic ones. Published in Nature Astronomy in 2023, the results were striking. Mineral salts and organic compounds sitting right on the icy crust. Chemistry with no obvious reason to be there, unless something from below had once reached the surface. The chemistry Juno found deserves one more beat of attention. Salts don't just appear on an icy crust by accident. Something has to deliver them there from somewhere below the surface. Cryovolcanism tops the list, so do cracks, or slow diffusion through the ice. Whatever the exact pathway, the salts had to come from underneath, two completely different instruments, decades apart, pointing at the same buried sea. That agreement is exactly what makes this conclusion so solid today. Two missions landed on the same answer, though built for entirely different purposes, decades apart, using completely unrelated methods. Zoom out for a second. Jupiter and its four largest moons could almost pass for a small solar system. Now zoom all the way back in, past 95 miles of frozen crust, down to a dark layer of salt water nobody has ever tasted or seen. Ganymede's hidden ocean is estimated at roughly 60 miles thick, buried beneath about 95 miles of solid ice. Some estimates suggest it holds more water than every ocean on Earth combined. Earth's deepest trench barely reaches 7 miles down. You'd need to stack nearly 9 of them end to end to match this depth. Every mile of it was inferred, not sampled, from a faint wobble of light. Try to hold that 60-mile figure in perspective. Stack nearly 9 Mariana Trenches end to end. You'd still fall short of this ocean's depth. All of it sealed under ice thick enough to bury Mount Everest twice over. Every drop of it inferred, never sampled, never seen. Unlike Europa's ocean, this one never touches a rocky seafloor. It's sandwiched between two layers of ice, top and bottom. That distinction matters for a specific reason, not just trivia. Rock can supply minerals and chemical energy an ocean needs to potentially host life. Ganymede's ocean touches only ice, above and below, with no obvious energy source. That doesn't rule life out, but it does lower the odds considerably. Scientists still rank Europa and Enceladus higher on that particular list. Here's what all three moons add up to. Io's volcanoes are ferocious, but fully explained by tidal squeezing. Europa's plumes may not even be real. Even if they are, they follow that same known mechanism. Only Ganymede produced an actual measured mismatch. 6 degrees promised, 2 degrees delivered. That mismatch never broke a single law of physics. It forced one to be applied more completely, using a variable nobody had directly measured before. The missing 4 degrees is now remote, non-invasive proof of an ocean. Nobody has touched it. Nobody has drilled into it or seen it directly. The measurement that looked like broken physics turned into one of its most elegant confirmations. Not a mystery left dangling, a puzzle closed by watching a faint red light. It refused to swing as far as the math demanded. Stop and notice what actually just happened here. A headline promising broken physics led you through 3 moons. Not one of them actually broke a single equation. That's not a letdown. That's how real science almost always plays out. The universe rarely hands us genuine paradoxes. Think about the sheer patience this required too. Years of watching a faint light, years of refining a single number, all to catch 4 degrees of difference, invisible to any naked eye. That's what real discovery usually looks like. Not a sudden flash of insight, but a slow accumulation of proof. The European Space Agency isn't waiting for more indirect proof. JUICE launched in 2023. Its full name, the Jupiter Icy Moons Explorer. It's now heading toward Ganymede. On board sit a magnetometer and radar, built specifically to map that ocean, layer by layer. The Aurora already told us the ocean is there. JUICE aims to finally show us its true shape. Ask yourself what else might be hiding this way right now. How many other measurements still look impossible today? Maybe only because we haven't found their hidden ocean yet. Ganymede answered one such question already. It almost certainly won't be the last. Somewhere above Ganymede's pole right now, that ribbon of Aurora still traces its shortened arc, still swinging only 2 degrees instead of the 6 the equations once promised. A quiet signature written in light, of an invisible sea, sealed beneath 100 miles of ice.